Welcome to another day of physics, and we are going to be continuing on with two-dimensional kinematics in preparation for the test. Last time, we did this question: what is the acceleration? I throw a ball at an upward angle. What is the acceleration of that ball in x and y after it leaves my hand? And we're using the notation where you have the x component in first and then the y component second. And last time we determined that the correct answer was D, that the acceleration in x is 0 and the acceleration in y is negative 9.8 meters per second squared. And we're going to use this a bunch for two-dimensional kinematics problems where we have multiple directions that we're dealing with, angles that we're dealing with. And the first one is kind of an evergreen question. This example: Kim Jong-un launches a rocket at an 80-degree angle to the horizon at 1,200 meters per second. Now, I didn't specifically say it here, but assume that the rocket is magical, because of course it is, and as soon as it leaves the ground, it is already moving at 1,200 meters per second at that 80-degree angle. The rocket is launched from sea level. How far away from the launch pad does the rocket land? Assuming, this is another thing that I didn't say in the problem, assuming that the rocket is launched from sea level and it lands at sea level, how far away does it land? Immediately going to 1,200 meters per second and at that 80-degree angle there. First thing to do in any question like this is actually draw it out. That's always a good idea, to draw out what's going to happen. I tell you that the initial speed of the rocket is 1,200 meters per second. So it's launched right there at 1,200 meters per second at that 80-degree angle. And it's going to make that kind of parabolic shape. Now, the book actually explains the book has one explanation for why it's a parabolic shape. I'll show you another explanation as we're doing the work here as to why it's a parabolic shape. You can find this picture in the slides, and you can find the video where I actually go through all this online as well. First thing that we always need to do when we're looking at a problem like this is determine if it's a one-dimensional problem or a two-dimensional problem. This certainly looks two-dimensional. If something is just going up and down, that's one-dimensional. If something is just going left or right, then that's one-dimensional. But if it's going at angles and moving in like, you can see components to it and those components are changing, then it's two-dimensional. So if it's two-dimensional, we can just start pulling out equations. Now, I know where this problem is going because I wrote this problem and I've had decades of experience doing this kind of problem. If you do not have decades of experience doing this kind of problem, that's okay. What you can do when you see a problem like this and you're asked, okay, how far away is it going to land? Like, okay, what does that mean? What does that mean? How far away is it going to land? Well, that's really this delta x thing. Delta x shows how far away it will land. It starts at sea level. It goes up at 1,200 meters per second, but gravity is trying to pull it back down, and so gravity pulls it back down, and it ends some distance away, and that distance away is in the x-axis. So we can say, I need an equation with a delta x in it. And this is an equation with a delta x in it, and hint, hint, this is going to be the thing that actually works for a problem like this. Delta x is equal to v naught x, which is the initial velocity in the x direction. That's what these subscripts mean. Sometimes you have to read these subscripts out of order. The 0 is the equivalent to the little I. If it's a little 0 or little I, that means the same thing. The 0 is kind of saying at time equals 0, and that's the beginning. If it's an I, that means that the initial state, which also means t equals 0, the time is 0. And so both the 0 and the I mean initial or time equals 0. So initially, the velocity in the x direction, that's what v naught x means. V naught x, initial velocity in the x direction. That means that we've got, actually it's convenient that I have these extra pieces of paper here. We've got an initial velocity vector that looks like that, say, and we'll get rid of that because that's confusing. And this angle is 80 degrees. Well, this has an x component and a y component. Oops, there, something like that. An x component and a y component to it. You can always think of these as kind of the shadows of this vector. And if you take this vector plus this vector, that'd be like picking this vector up, plopping it down there, and it would equal out to that vector. Now, I do have some questions. Question from Nicholas. So we need to calculate how long it takes for the velocity to drop to 0 and start heading downward to know how long it's in the air, since it goes up and down at the same rate. Yes, that is one way of doing this. I'm going to show you a very, very slightly easier way of doing this. Spencer asks, would the same velocity in the y direction also be 1200 meters per second? So you're going to have one component in x, and so this x component is going to be 1200 times, let's see, the x direction is usually sine, oh, sorry, no, it's not, it's cosine. What am I doing? I had to remember SOHCAHTOA. Always remember SOHCAHTOA. 1200 cosine 80 degrees. This is going to be v naught x. V naught y is going to be 1200 sine 80 degrees. This is, of course, very important for getting this kind of question correct. V naught x is going to be the x component of this vector v. This is my initial velocity, and so the initial velocity is equal to 1200 meters per second. And so the x component is 1200 times the cosine of 80, and the y component is 1200 times the sine of 80. If this does not make sense to you, first read that chapter from the book. It's, I think, 1.7, section 1.7, somewhere in there. Read that section out of the book and work on this, work on understanding this. This equation up here is the same as our initial equation. Delta x is equal to v naught t plus 1/2 at squared, except I made it specifically for the x direction. See, I put little x's down there. When you've got the, let me do this. When you've got different directions that you're dealing with, you need to be specific, saying that we're talking about the x direction for the initial velocity, the x component of the initial velocity, and the x component of the acceleration there. The x acceleration, as we demonstrated on that previous problem, is 0. We've got no acceleration in the x direction. We have not talked about forces yet, but the only thing that can cause an acceleration is a force. And the only force that we're dealing with in this problem is the force of gravity, and gravity pulls down. So that's going to be a negative y force. There are no forces acting in the x. And so this is going to be 0. And so that means that we can completely disregard this whole term for x and just say that delta x is equal to v naught t. Well, that's going to help us a lot if we can figure out what v naught x is and what t is. We really already did figure out what v naught x is. We figured it out here because that's something your calculator can tell you what it is. If we can figure out t, then we've got it. And this is what Nicholas was getting after. Well, we don't know what t is yet. So instead, let's do the same thing, but with our other dimension. We did this for x now. We're looking for what delta x is. Technically, it looks like I don't even need to deal with delta y, but when you've got two-dimensional problems like this, almost certainly you're going to have to deal with both directions. You're going to have to deal with x and you're going to have to deal with y to solve any problem like this. So let's just write it out again. Let's just say this, instead of delta x is equal to stuff with x in it, let's say that delta y is equal to stuff with y in it. Delta y is equal to v naught y. That's going to be the initial velocity in the y direction, which is this. If you've got this as your initial velocity, then this is your initial y velocity. So initial y velocity times the time. Now, time has no subscript to it because the time in x is the same thing as the time in y. We don't have different times in different directions. That would be a very strange universe. Then we add 1/2 times the acceleration in y times t squared. Acceleration in y is negative 9.8 meters per second squared. V naught y is what we figured out here, right there. Excuse me, I'll point this way. Figured that out right there. So we can say instead delta y is equal to v naught y, which we really already calculated, and we can just plug that in whenever, times t minus 1/2 gt squared. I replaced a y with negative g. So the negative went out there, and we have the g there. We get v naught x, v naught cosine theta, plug in the numbers, 208.4 meters per second. V naught y, we do the exact same thing with sine instead of cosine using SOHCAHTOA, and we get that. Oh, I do have a question from Paul. Why is g negative? This is a good piece of paper to work on this random extra stuff on, so this works. We define g to be 9.8 meters per second squared. Like we say, g is equal to that. We don't put a negative on it there. This is how this book does it, and this is how most physics books do it. But we know that gravity pulls down, and so when you drop something, then it accelerates downward at 9.8 meters per second squared. So we need to remember that it is 9.8 meters per second squared down, which gets us to negative 9.8 meters per second squared. So when we have to plug gravity in, when we're just writing about what gravity is, what the acceleration due to gravity is, we write it as 9.8 meters per second squared. When we plug it into an equation, we have to remember that it's pointing down. It's usually a good idea to remember that it's pointing down here, but that's the difference between this is really a scalar right here. The acceleration due to gravity is a scalar because we're not really specifying direction. We know what the direction is because we live on Earth and we drop things and we know that it's down. When we do it mathematically, we have to remember that negative. When we plug it into an equation, we have to remember the negative in there. Any other questions? Oh, follow-up. And the acceleration in x direction is positive. Remember, there is no acceleration in x. There's a velocity in x because there's, you have this velocity vector like that, and you break it up into the x and y. So there's an initial velocity in x, but because there's no forces in x, then, because there's no forces in x, you don't have any acceleration in x. We will eventually learn that F equals ma, and Fx equals max. The forces in x, this is actually the net force, the sum of the forces in x will equal to the mass times the acceleration in x. If there are no forces in x, then there can be no acceleration in x. So there's actually no acceleration in x here. There's only acceleration in y. Any other questions right now? In a real physics equation, not like a theoretical homework problem, would you include air resistance going in the x direction? Yeah, probably. You would probably include the air resistance in the x direction. Certainly, any one of you that's an engineer, you're going to have to include air resistance in your, like aerospace engineering certainly will require air resistance. And we might have time at the end of the semester to talk about air resistance. The equation for air resistance, in case you're wondering, is usually some function of some constant times the velocity squared. And so as you increase the velocity, if you double the velocity, then the amount of air resistance is actually increased by a factor of 4, because you plug in 1 there versus 2 there, then it would go up by a factor of 4. If you're going 10 times faster, you have 100 times the air resistance. And then that all goes crazy once you break the sound barrier. Like all this just, none of it works around the speed of sound. So air resistance in the real world is really interesting stuff. I hope that we have a little bit of time at the end of the semester to work on that because it's just so interesting. Anyway, we've got all that now. And what can we do? Well, we can plug all this stuff in. We can plug in 208.4 in right there. We can plug in 1181 in right there. We can plug in 9.8 in for G. And we still don't have enough. We'd actually have 2 equations and 3 unknowns so far. Because we don't know what delta x is, we don't know what t is. Delta y, we'll have to think about delta y, and then t again. Actually, do we know what delta y is going to be in this problem? Type into chat if you think you know what delta y is going to be for this problem. Hey, yeah. Delta y is going to be 0. It's launched from sea level. It lands at sea level. That means the change in y. Delta means the change in something. This is the change in the y position. The y position starts off at sea level. It ends at sea level. Delta y is 0 for this problem. That's real convenient, actually. So we can look at what that makes our equation do. This is plugging in the numbers that we know. I plugged in I plugged in v naught y in there. I plugged in negative 9.8 in for g. And then delta y is 0 because it's at the same height. And so I can solve for t. I have a higher resolution image in the PowerPoint slide, so check that out if this is hard to see. If I plug in 0 there for delta y, then this becomes 1 equation and 1 unknown. 0 equals 1181 times t minus 1/2 times 9.8 times t squared. I can solve for t pretty quick with that. And so I can find that the time is 241.2 seconds. Now, what on earth does that mean? Well, we plugged in delta y is equal to 0. So really what we're looking for is the time when delta y is equal to 0. If we define this point to be the initial point of the problem and that point to be the final point of the problem, then delta y is 0 because we didn't change our height, or we returned to the same height more precisely. And the time that it took for that to happen ended up being 241.2 seconds. That's what we can do in this kind of problem. We can solve for when particular events should occur. Shouldn't the time in the x direction and the y direction be the same? Yes, the time in x should be the time in y, and that's why I do not have a little y there and a little x there, because they are the same times in each case. Because we don't have x time and y time, which make our universe very strange and confusing. So now I can take this time and plug it into delta x. And so if I plug that in there, so I take the 241.2 seconds, I plug it in there, I take the v naught x, I plug that in there, it's just going to be 208 times 241. And 208 times 241 is 50,260 something, but I abbreviated that as 50.26 kilometers. On a test, I'll always tell you what units that you should be using. If there's ever going to be a confusion about what units to use, I will tell you what units to use. So I could have just as easily written 50,260 meters in here, but why do that when you can write kilometers? It's good to get practice converting between those. In the YouTube channel that I have created, I have a video which explains everything that we just did. And I have, in that same video, I have a version where we solve it in a completely different order. I start off telling you that it lands 50.26 kilometers away from the launch point, and I tell you that it's still at the same angle, and I ask you to find the initial velocity. And I do all the math to show you how to find, if you're given a different set of initial conditions, instead of being told, as we had before, initial velocity and angle and find delta x. Well, what if you have delta x and angle but need to find initial velocity? Can you do that? The answer is yes. It takes about that much math, and it gives you the exact same answer that you had before. So check out that video on YouTube. I recommend that you subscribe to the channel for the duration of the semester just to see what's there. I plan on leaving those videos up forever and ever, so you can always come back and check them out if you ever need to. If you have questions on this, then email me, but watch that video. Watch the video and then email me. You can see that I include all this stuff on the PowerPoint slides, and all that at hopefully a little bit higher quality, and I give you the link to the video there on the PowerPoint slides. I've got some problem-solving strategies to help you to be able to do this kind of problem. And briefly, what's involved in these problem-solving strategies? I never want to give you just a list of steps. Every problem is going to be the same. And so giving you a list of steps and telling you just memorize this list of steps, well, for every different type of problem that you'd have a different set of steps, and you'd have to memorize like 50 different sets of steps to get every kind of problem right. It's better to have strategies rather than steps. And so what strategies can we do? Well, we can start by drawing a picture. It is never a bad idea to draw a picture of what's going on. It helps you visualize what's happening. We're all built to be able to visualize these kinds of things. And so drawing that picture starts you up in being able to visualize what's going on in a problem. What x coordinate does it start at? What y coordinate does it start at? You can look and see, where should I set my origin point? That can help you start thinking about, okay, what is initial positions, and then what kind of final positions are you going to have? That's another one of these steps. What x coordinate does it end at? What y coordinate does it end at? Thinking about that will help you determine where you should set initial things and final things. You can look at what x velocity it starts with, what y velocity it starts with. You'll very often be given a velocity at a particular angle. And whenever you see a velocity at a particular angle, you can say, well, I probably have to break it up into x and y velocities anyway, so why not just do it at the beginning? What's my acceleration in x and what's my acceleration in y? If you've got a projectile, if you've got something flying through the air that's just being pulled down by gravity, you'll probably have 0 acceleration in x, negative 9.8 meters per second squared acceleration in y. What x coordinate does it end at? What y coordinate does it end at? That's, again, just looking at the final conditions of the problem. What x velocity does it end with? What y velocity does it end with? Sometimes you'll be given problems where you have to look at the final velocities. Say that you know that something hits a wall at 14 meters per second. Some water balloon hits the wall at 14 meters per second. Well, then you can figure out x velocities and y velocities at the end of the problem from that kind of thing. How long does it take to do its thing? You might be given, hey, this rocket took 241 seconds to land, or you might have to solve for that. All of these things can be things that you are given at the beginning, or things that you can deduce. Like in this case, I never told you delta y is 0. I just said it starts at sea level and it ends at sea level. And so you deduce from that that delta y is 0. Another deduction can be, oh, I need to figure out what time is. If I can figure out the time that it took to hit the ocean, then I can get the rest of the problem done. And so solving for t, solving for time, can be very important. There might be other clues hidden in there somewhere. And try equations one dimension at a time. What did we do? We said delta x is equal to v naught x t times plus 1/2 at squared, and delta y is equal to v naught y t plus 1/2 ay t squared. And so we looked at this problem one dimension at a time using the equations that we've already been given. Here's a fun one, I think. We are defending against pirates. We've got Castillo de San Marcos. That's the castle fort thingamajig in St. Augustine, which is about 2 hours north of here, 3 hours north of here, something like that. It has cannons that are about 18.5 meters above sea level. I actually went into Google Earth to try to figure that out. And as best as I could tell, yeah, it's something about 18.5 meters above sea level. That is obviously not exact, and the error bars on that would be very large, but it's something like that. If you fire a cannonball at a speed of 130 meters per second at an angle of 25 degrees above the horizon, how far away will that cannonball land? Now, of course, this is assuming that it hits the water in the ocean, and you can deduce from that what the y and such have to be. And one of the things that I did want to mention here is at this point in creating these lectures, I realized that this version of the book changed the way that it expresses this equation. This equation I had been writing as delta x, instead of x final there, I'm looking at the fourth equation here. Instead of x final, the previous version of the book had delta x is equal to v naught xt plus 1/2 axt squared. Well, this version of the book has x final is equal to x initial plus v naught xt plus 1/2 at squared. It's the exact same equation. Delta x is equal to x final minus x initial. So imagine having delta x here and replacing it with x final minus x initial, and then adding x initial to both sides. It would get rid of the x initial on this side and put it over there. And so you really do have the exact same equation. I actually prefer this equation to the previous one because I like being able to see my x final and my x initial as different things. You can use whatever you want because they both work, because they're the exact same thing. But I do kind of like this variant of the equation a little bit better. It makes it a little bit easier to see, I think. Well, the hint I give you is what is y initial and what is y final in this case. Actually, can anyone answer that? What is y, let's say, what is y initial going to be? What do you think y initial will be in this problem? 0. That's a possibility. Anyone else have a guess? What is y initial? Okay, so Nicholas says that y initial could be 0 and y final could be negative 18.5. Yeah, so that would be setting your origin point at the place where the cannonball is originally fired. Alternatively, you could say that the cannonball starts at 18.5 and ends at 0. That would be using the surface of the ocean as your origin point. They will both give you the exact same answer. So we can do either. You can probably tell that my handwriting is a lot better when I can go slower through it. And so that's why I write out all these things beforehand, because my handwriting is bad enough as it is. I'm going to cover things up again just to be that kind of guy. And I look at what we've done. I've drawn it out. Even I've been doing this for literally decades, and I always start with a drawing. It's not to be patronizing to you to start with a drawing. It's because I draw these things whenever I have to do any kind of problem like this. Even to me, after so many decades of working on this stuff, yeah, this problem is kind of simple. But I still draw it out because it really helps me think about it. So I give you all the initial conditions here. I say, let's find the point x final there. And I give you an initial velocity and an angle, so why not figure out v initial x? See, I changed another thing. I went from having a 0 there to say that this is what the time equals 0 velocity in the x direction is. I changed it to I, which means initial. And I wanted to do that because, man, there are so many different versions of all these different books that all have different subscripts. And you're going to have different subscripts in your engineering courses or your astronomy courses or whatever else you have, that it's good to get used to having different kinds of subscripts there. So the initial velocity in the x direction is equal to the initial velocity, 130 meters per second, times the cosine of our angle, which is measured from the positive x-axis, and that's 117.8 meters per second. Our initial velocity in the y is just going to be the same thing with sine instead of cosine, 54.9 meters per second. Then we can take our equation. We are taking our new version of that equation that I just showed you, which is the equation in this edition of the book, unlike the last edition. X final, which is what we're looking for, is equal to x initial, our initial x position, which I'm just going to say is 0. Let's just say that our initial x position is 0, because that's easy. We start off at a position of 0. We're trying to figure out how far away it is, and so if it doesn't move, then that's 0 right there. Plus the initial x, which we figured out there, times the time, plus 1/2 times the acceleration in x, which is 0, because once the cannonball leaves the cannon, there's no more forces acting on it other than air resistance, but we are completely ignoring air resistance for now because that overcomplicates everything. So to do air resistance justice, you need to be able to plug it into a computer, which we're not going to do this semester. We're not going to solve those in that in-depth. So this should be 0. And we can write that down. X final is equal to 0 because we're taking our initial x to be 0, plus the initial x, which we figured out down here, times the time, which we don't know, plus 0 because this whole thing is 0. Well, we can't really finish that because we need to know that, we need to know that. So we do the same thing in y, take the new variant of that y equation and plug in what we know. The way I'm going to do it is by having the initial position be positive 18.5 meters and the final be 0, but there's no difference between that and what Nicholas said in chat. And so we get y initial is 18.5, y final is 0, v initial y is 54.9 meters per second, times our unknown time, minus 1/2 times 9.8, because ay is equal to negative g, and so we've got negative g times t squared. This is a quadratic equation, or we need the quadratic equation to solve that, unfortunately. And so I recommend getting a calculator that can do it for you, and you would find that the answer is either 11.54 seconds or negative 0.327 seconds. This doesn't make any sense. It does not make sense that it would land before you launched it, and so we can ignore that and say, well, it's got to be that. Right there, 11.54 seconds. We then plug the 11.54 in there, so we get 117.8 times 11.54, and we get that x final is equal to 1359 meters. The equation that I gave you before was delta x is equal to v0 xt plus 1/2 axt squared. Now, at some point, I said that v0 is the same as vi, because that means the time or the velocity at time equals 0, and that means the velocity initially. The O and the I actually mean the exact same thing in different books. The other change, I just want to write this down just in case. The other change is I changed delta x into x final minus x initial equals v naught xt plus 1/2 axt squared, and then I added x initial to both sides, and that got x final is equal to x initial plus v naught xt plus 1/2 axt squared. So those are the two changes that I made to that original question, or sorry, that original equation, that I do want to make sure that you can see that, yes, it is different, but it actually means the exact same thing.